Hello, this is the first video of the second order differential equations 3 series on modelling with second order differential equations for OCR Pure Core Further Mathematics, and it introduces simple harmonic motion. Here is a mass on a spring. And here a pendulum. And here possibly a combination of both. These are all examples of simple harmonic motion. So a mass bouncing up and down on the end of a spring would have equation dtx by dt squared equals minus k over mx, where k is the stiffness of a spring and m is mass. A simple pendulum dt theta by dt squared equals minus g over L theta, where g is acceleration due to gravity and L is the length of string. You may have come across these in physics lessons or had a personal experience if you've ever done a bungee jump. Many other real-life situations have an oscillating motion that can be modelled by equations of the form d2x by dt squared equals minus omega squared x. If we use the auxiliary equation method that we've come across in previous series, we will see that we'd have m squared equals minus omega squared, so m will equal plus or minus omega I. And this will lead us to the standard general solution of x equals p cos omega t plus q sine omega t for when the roots of an auxiliary equation are purely imaginary. You should link this with your work on trigonometry, in that we can write a cos theta plus b sine theta as being some r sine theta plus alpha. Therefore, we can write that general solution in the form that x equals a sine omega t plus epsilon, where a is the square root of p squared plus q squared, and tan epsilon equals q over p. Since sine theta varies between minus 1 and 1, then x will vary between minus a and a. Hence, a is the amplitude of the curve. Sin t is periodic with period 2 pi, hence the solution has period 2 pi over omega. Epsilon is called the phase shift and has the effect of translating the curve to the left by epsilon over omega. We can see the effects of altering the constants a, omega and epsilon. So altering a, we can see alters the amplitude of the solution curve x equals a sine omega t plus epsilon. If we alter omega, we can see that that alters the periodicity. And if we alter epsilon, we can see the effect of that phase shift. In the next video, we will consider damped oscillations.